Good evening, and welcome to The Sleepy Scientist. This is the quiet corner of the internet where science and rest meet, where gentle stories about our world and beyond are told slowly enough to ease you into sleep. Tonight's journey takes us beneath our feet, to a world that seems still but is never truly at rest. The topic is the restless Earth, a planet whose surface is forever shifting, drifting, and colliding in a dance so slow we hardly notice, yet so powerful it has shaped every mountain, ocean, and valley we know. Before we drift any further, I would love to know, where in the world are you watching from, and what time of night or morning is it for you? It is always a wonder to imagine this shared experience stretching across time zones and continents. If you enjoy these quiet explorations, a gentle tap on the like button helps the channel more than you might think. If you're already subscribed, thank you for joining this sleepy little community. And if not, feel free to subscribe and click the bell so you don't miss the next calm voyage into science. Now, I should probably warn you, I hope this video isn't so interesting that it keeps you wide awake. But if it does, then at least you'll come away with some surprising knowledge to carry with you into tomorrow. So settle in, let the outside world soften, and let the story begin. Have you ever wondered what secret motions are happening deep beneath the ground you walk on every day? The Earth may feel solid and still beneath your feet, but in truth it is a restless traveller. Its surface is made of giant slabs, tectonic plates, that drift slowly but ceaselessly, reshaping the planet as they move. These drifting pieces of Earth's crust are older than any human civilization, and yet as alive with motion as the waves of the sea. In this calm exploration, we will unfold the story of these plates, how they were discovered, how they move, and how they have carved the face of the world. This is a tale of fire rising from the mantle, of continents pulling apart and colliding, of oceans born and mountains raised. It is also the story of how the hidden movements beneath us shape climate, guide the path of evolution, and even influence the myths that humans tell to explain trembling ground. The beauty of plate tectonics is not only in the science, but in its patience. While our lives play out in days and years, the Earth moves in spans of millions of years, quietly sculpting landscapes we take for granted. Tonight we will let those timescales stretch out before us, moving as slowly and steadily as the Earth itself, pausing where the science is curious, and lingering where the imagination can take comfort. The restless Earth is not something to fear, but something to marvel at. It reminds us that even in silence and stillness, the world is alive with motion. As you drift further into this story, let the thought of mountains rising, seas opening, and continents wandering be a quiet companion to your own journey into rest. In the beginning, Earth was a place of fire. Imagine a young planet still glowing with the heat of its own birth, a ball of molten rock circling a young sun in a solar system full of chaos. Asteroids and comets crash down with relentless fury, stirring the surface and keeping it in a state of liquid turmoil. To stand there, if one somehow could, would be to witness a world in the making, a world too hot for oceans, too violent for life, and yet full of the raw materials that would one day build mountains, forests, and even ourselves. The planet formed about 4.5 billion years ago from the swirling dust and gas left over after the sun ignited. Gravity pulled this debris together bit by bit until clumps of rock collided and fused, growing into something large enough to be called a world. Those collisions were not gentle. Each impact released colossal amounts of heat, enough to keep the entire planet glowing red, like a furnace without end. Heavier materials like iron and nickel sank inward toward the core, while lighter rocks floated upward, eventually becoming what we now call the crust. Slowly, as the bombardment lessened, Earth began to cool. The surface hardened in patches, though molten rivers of lava still cut across it. This early crust was fragile, constantly broken apart and remade. It was more like a cracked skin than a stable surface. Beneath it, the mantle churned with heat, and above it, the thin beginnings of an atmosphere took shape, not one you would ever want to breathe. Instead of oxygen, it was thick with carbon dioxide, methane, and ammonia, the byproducts of volcanic eruptions that sent plumes of gas spilling into the sky. Lightning crackled through this toxic haze, striking down into pools of lava and boiling seas, and yes, seas. For all the fire, there was water. Some of it came from volcanic steam that condensed into rain, falling for millions of years until it collected in low basins. Some of it was delivered by icy comets that struck Earth and melted away, leaving behind vast amounts of liquid water. Together, these sources filled the first oceans, perhaps shallow at first, but spreading wider and deeper as time went on. To imagine those first rains is to picture clouds that never parted, sheets of water falling onto a world still trembling with heat, hissing as it struck the half-cooled crust. Out of this meeting of fire and water, the surface of Earth slowly settled into something recognizable as a planet rather than a cosmic battleground. With oceans came change. Water softened the land, carving channels, breaking apart rocks, and carrying minerals back to the sea. Chemistry began to stir in ways that would one day lead to life, though that was still far in the future. For now, Earth was an infant world, covered by volcanic islands, restless seas, and skies filled with storms. The continents we know did not yet exist, but their foundations were forming, blocks of lighter rock rising above the heavier oceanic crust like rafts on a molten sea. If one could look from space at that time, the Earth would have appeared very different from today. There were no wide continents stretching across the globe. Instead, there were clusters of rocky fragments, shifting and colliding, merging into larger landmasses. It was a restless puzzle still being put together. These early movements hinted at the drifting of continents that would one day become the slow heartbeat of geology. The crust was not a single solid piece, but a mosaic of parts, nudged and jostled by forces deep inside the planet. This was the beginning of something extraordinary, the restless nature of Earth itself. Unlike Mars with its quiet, frozen surface, or Mercury, locked in silence near the Sun, Earth was set apart by its ability to change. The crust was thin enough to crack, the mantle hot enough to flow, and the core powerful enough to drive motion for billions of years. These conditions ensured that our planet would never remain still, that mountains would rise, oceans would open, and land would wander. The young Earth was both hostile and generous. Hostile because of the endless volcanic eruptions, the poisonous air, and the meteor strikes that scarred its surface. Generous because within this chaos it forged the elements of a stable crust, the waters of oceans and the air that would slowly shift towards supporting life. It was a world finding balance, though balance in geology is never still. It is a balance of moving parts, of stone and water trading places, of heat and pressure locked in a dance. Even the moon played its part. Born from a colossal collision with a Mars-sized body, the moon's gravity helped steady Earth's tilt, calming what might have been a wildly unpredictable spin. Tides began to move in the young oceans, pulling water back and forth, shaping shorelines and stirring chemical reactions. In this way, even the heavens contributed to the restless story of Earth. When we look at the ground beneath us now, it can feel immovable, ancient, and eternal. But the first hints of continental drift remind us that this is an illusion. Beneath the stillness lies motion. The continents may move only a few centimeters each year, slower than your fingernails grow, but over millions of years that is enough to reshape everything. The mountains, valleys, and seas we see today are the end result of that first fiery beginning, when Earth decided it would never be truly still. The story of fire and stone is the story of a planet that cooled just enough to harden, but never enough to fall silent. A place where oceans gathered, where the crust cracked and shifted, and where the seeds of continental drift were first planted. It is a reminder that even in the slowest processes, in the quietest shifts, there is power beyond measure. The young Earth may be long gone, but the restlessness it began still hums beneath our feet, guiding the shape of the world we live on. At the dawn of the 20th century, the world seemed neatly mapped and understood. Continents were drawn, oceans named, mountains catalogued. The Earth, people thought, was solid and still, its great land masses fixed in place for all of history. Yet one man looked at those maps and saw something others overlooked. Alfred Wegener, a German meteorologist with a curious mind, noticed that the continents seemed to fit together like pieces of an ancient puzzle. South America's eastern coastline curved neatly into the bulge of Western Africa. It looked less like coincidence, and more like evidence of something deeper. Wegener began to wonder, what if the continents had once been joined together? What if they had drifted apart, carried across the surface of the Earth by some unknown force? This idea, bold and strange for its time, would become known as the theory of continental drift. It was not the first time someone had suggested the continents might have moved, but Wegener was the one who gathered the evidence and gave the idea structure. He collected fossils that told a curious story. Identical species of plants and animals, long extinct, were found on continents now separated by vast oceans. How could a tiny reptile from the Permian period, called Mesosaurus, appear in both South America and southern Africa, unless those continents had once been connected? He looked at ancient rocks and mountain ranges, which seemed to line up perfectly when the continents were reassembled. He even studied ancient climates, pointing out that evidence of glacial deposits in India, Africa, and South America made sense only if those lands had once been closer to the South Pole. The picture was convincing to him. Wegener proposed that all the continents had once been united in a single supercontinent he called Pangaea, all Earth. Over millions of years, he said, this massive landmass had split apart with pieces drifting slowly to their present positions. It was a daring thought. The problem was Wegener could not explain how such a monumental drift was possible. What force could shove entire continents around? His answer, vague at best, was that the continents ploughed through the oceanic crust like icebergs through water. Geologists were unimpressed. To them, the Earth's crust was solid and immovable. The idea of continents wandering across the globe sounded absurd, more fantasy than science. Wegener's theory was ridiculed, dismissed as the dream of a man who studied weather, not rocks. At conferences, he was treated with skepticism, sometimes with open laughter. One American geologist declared that Wegener's theory was utter damn rot. Another quipped that if the continents really did drift, the force pushing them would be the wrath of Almighty God. It did not help that Wegener's timing was poor. In the early 20th century, geology was built upon the assumption of a static Earth. Mountains were thought to rise from the planet shrinking as it cooled, like wrinkles forming on a drying apple. Oceans were considered permanent fixtures. To challenge these foundations was to challenge the very identity of the field. Wegener's critics were not just protecting ideas, they were protecting the pride of a discipline, and yet Wegener's evidence lingered. The fossil trails, the matching rocks, the puzzle piece continents, they did not go away simply because people ignored them. The seeds of his idea lay dormant, waiting for a new generation of discoveries to bring them to life. Wegener himself would never see that happen. He died in 1930 during an expedition to Greenland, his theory still considered a fringe idea. But science, like the Earth itself, is restless, and truth has a way of resurfacing. The turning point came in the mid-20th century, when technology allowed humanity to peer into the depths of the oceans. During and after the Second World War, navies mapped the seafloor in detail for the first time. What they found astonished them. Running down the middle of the Atlantic was a vast mountain chain, thousands of kilometers long, called the Mid-Atlantic Ridge. Similar ridges appeared in other oceans. The seafloor, far from being a flat, lifeless plain, was a landscape of mountains, trenches, and valleys. Even more remarkable were the patterns in the rocks of the seafloor. As scientists studied the magnetic properties of oceanic crust, they discovered something odd. The iron-rich minerals in volcanic rocks aligned with Earth's magnetic field when the rocks solidified. But Earth's magnetic field had flipped many times in the past, north becoming south, and then back again. The seafloor recorded these flips as stripes of alternating polarity, running parallel to the ridges. Each stripe was a magnetic memory, frozen into stone. This striped pattern revealed something extraordinary. New crust was forming at the ridges, pushing outward as molten rock rose and cooled. The seafloor was spreading, carrying the continents with it like passengers on a slow-moving conveyor belt. Suddenly Wegener's drifting continents made sense. They were not ploughing through solid crust. They were riding on slabs of rock created and destroyed by deep earth processes. The pieces came together in the 1960s, as the theory of plate tectonics emerged. Wegener's once ridiculed idea was reborn, now with the physics and mechanics to back it up. The continents did drift, but they were part of larger plates, moving on the restless mantle beneath them. Mountains, earthquakes, volcanoes, and ocean basins could all be explained through this framework. What once seemed laughable became the cornerstone of modern geology. Looking back, it is easy to wonder how so many scientists missed what now feels obvious. But that is the nature of discovery. Ideas too bold for one generation can become the foundations of the next. Wegener was not alive to see the vindication of his work, but his legacy is carved into every geology textbook and every map of tectonic plates. His vision of a dynamic Earth, shifting and changing, opened the door to a new way of understanding the planet. There is something poetic in this story. A man staring at maps dared to imagine the continents wandering across time. His peers laughed, but the Earth itself had the last word, whispering its truth through magnetic stripes on the ocean floor. Today, as we stand on what feels like solid ground, we know it is anything but. Beneath our feet lies motion, proven not by imagination alone, but by the hidden patterns of stone, recorded patiently over millions of years. The invention of tectonics was not a single spark, but a slow gathering of evidence, the gradual turning of skepticism into acceptance. It reminds us that science is never finished. What we dismiss today may be tomorrow's truth, waiting quietly beneath the surface until we are ready to listen. Just as the continents drift, so too does human understanding, carried along by curiosity and time. Beneath your feet lies a puzzle so vast and so slow-moving that it takes the span of millions of years for a single piece to slide into place. The surface of Earth, which feels so solid and unshakable, is in truth a mosaic of plates. Imagine the planet as a cracked eggshell, though one that is constantly being reshuffled by heat from within. These fragments are the tectonic plates, and together they form the restless skin of our world. There are 7 giant plates that dominate the surface. The African plate stretches across deserts and jungles, carrying the vast continent and pushing into the Atlantic Ocean. The North American plate holds not just the continent we know, but also much of the Atlantic seafloor. Its partner to the south, the South American plate, drifts westward toward the Pacific. The Eurasian plate is immense, spanning from the Atlantic all the way across to Asia, locked in a slow-motion dance with its neighbors. Beneath the Pacific itself lies the largest plate of all, the Pacific Plate, a slab of rock so vast it covers nearly 1/3 of Earth's surface. Then there is the Antarctic Plate, circling in icy solitude, and the Indo-Australian Plate, which some geologists divide into 2, the Indian and Australian plates, each playing their part in mountain building and ocean spreading. But the story does not end with these 7. Around their edges cluster smaller plates, fragments and slivers caught in the grinding gears of geology. The Nazca Plate off the west coast of South America, the Cocos Plate near Central America, the Philippine Sea Plate, the Caribbean Plate. These and many more remind us that the planet is not neatly divided into just a handful of pieces. It is a living puzzle with dozens of parts, some large enough to carry whole continents, others just shards slipping between giants. What makes this puzzle extraordinary is not just that the pieces exist, but that they are always on the move. Each plate drifts a few centimeters every year, carried by the slow churning of the mantle below. Over human lifetimes that motion is imperceptible, but over geological time it adds up to the shifting of entire oceans and the birth of towering mountain ranges. The edges of the plates are where the drama unfolds. Far from being quiet seams, these boundaries are zones of creation, destruction, and transformation. There are 3 main kinds of edges, each with its own character. At divergent boundaries, plates move apart. Here, new crust is born as molten rock wells up from below, hardening into ridges that stretch across the ocean floor. The Mid-Atlantic Ridge is the most famous example, a scar running down the middle of the Atlantic Ocean, where Europe and Africa slowly drift away from the Americas. It is hard to imagine an entire ocean widening before our eyes, yet each year the Atlantic grows just a little wider, its edges pulled apart by this invisible force. Then there are convergent boundaries, the great collisions of geology. At these edges, plates push against one another, and something must give. Often, the denser oceanic plate sinks beneath its lighter continental partner, plunging into the mantle in a process called subduction. This recycling of crust fuels chains of volcanoes, like those that ring the Pacific in a fiery horseshoe. In other cases, when 2 continents collide, neither is willing to sink. Instead, the land crumples upward, forming mountain ranges that seem to defy time itself. The Himalayas, the tallest mountains on Earth, are the direct result of the Indian plate pressing into Asia, a collision that continues to this day. The third type of boundary is transform, where plates slide past each other. There is no creation or destruction of crust here, only grinding motion. These edges are notorious for earthquakes, as stress builds along faults until it is released in sudden jolts. The San Andreas Fault in California is perhaps the most famous example, where the Pacific Plate slides northward past the North American Plate, carrying Los Angeles ever closer to San Francisco, though only at the pace of a fingernail's growth each year. Each boundary type has its own story to tell. Divergent zones create, convergent zones destroy, and transform zones shuffle. Yet together they form a balanced system, a restless cycle of renewal and change. Without them, the surface of Earth would be stagnant, lifeless, a silent shell like the crust of the moon. Instead, the puzzle pieces grind, stretch, and collide, giving rise to earthquakes, volcanoes, and mountains, and keeping the planet's surface young and ever-changing. It is at the boundaries that we see the pulse of the Earth most clearly. Along mid-ocean ridges, black smokers belch superheated water into the deep, feeding ecosystems that thrive without sunlight. Along subduction zones, deep-sea trenches mark the descent of crust into the abyss, while arcs of volcanoes rise above, their eruptions both destructive and creative. Along transformed faults, cities tremble as the hidden stresses of geology are released in an instant. These edges remind us that the Earth beneath our feet is not a passive stage but an active participant in the story of life. The great puzzle of tectonic plates is one of the most elegant discoveries in science. It unites seemingly separate phenomena, earthquakes, volcanoes, mountain ranges, and ocean trenches, into a single interconnected framework. What once looked like unrelated mysteries are now understood as different expressions of the same underlying restlessness. To picture Earth's surface as a puzzle is to appreciate its complexity. Each piece is distinct, yet none can move without affecting its neighbors. The Pacific Plate collides with South America, raising the Andes. The African Plate splits apart in East Africa, birthing a new ocean in the making. The Antarctic Plate spins quietly at the bottom of the world, edged by a necklace of spreading ridges. Every boundary tells a story, and together they write the history of our planet. And yet, despite how much we know, there remains something mysterious in this puzzle. The plates are vast beyond comprehension, moving with patience that defies human timescales. To us the ground is steady, but to the Earth it is in constant flux. The restless boundaries where the action happens are invisible most of the time, hidden beneath oceans or buried beneath mountains, yet they shape every landscape we see. It is easy to think of puzzles as something finished once all the pieces are placed, but Earth's puzzle has no final picture. It is a work in progress, endlessly rearranged, never complete. The pieces slide and grind, split and collide, creating new shapes and erasing old ones. The puzzle beneath us is alive, and in its slow, ceaseless shifting, it reminds us that nothing on Earth is truly fixed, not even the ground we stand on. Deep beneath the crust, far below the continents and oceans, lies the true engine of Earth's restlessness. To the human eye, the mantle is hidden, invisible, a place of silence. Yet in reality it is anything but silent. It is a slow, swirling ocean of rock, not liquid exactly, but soft enough under pressure and heat to flow like warm wax. This vast mantle, stretching nearly 3,000 kilometers from crust to core, is what keeps the plates above in motion. Without it, Earth would be still, a cold and lifeless shell. The mantle is heated from below by the core, where temperatures rival the surface of the sun. That heat does not stay put. It rises upward in giant currents, just as steam lifts from a boiling pot or warm air drifts toward the ceiling. Rock in the mantle behaves the same way, though at a speed that would make glaciers look quick. Hot material slowly rises, cooler material sinks, and this convection sets the surface drifting like rafts on a sluggish tide. It is strange to think that something as solid seeming as stone could move in such a way. But under immense pressure and at extreme temperatures, rock is not rigid. It creeps, stretches, and bends. Over millions of years, it behaves more like a thick liquid than a brittle solid. Imagine honey left in a jar on a warm day, barely flowing yet never truly still. This is the mantle, patient, powerful, and endlessly stirring. From these currents arise plumes, narrow upwellings of superheated material that punch their way through the mantle and into the crust above. When one of these plumes reaches the surface, it creates hotspots, fixed points of volcanic activity that burn through moving plates. The Hawaiian Islands are a perfect example. As the Pacific Plate drifts northwest, the hotspot stays put, creating a trail of volcanoes that form a chain across the ocean. Each island is a marker of where the plate once sat above the plume, like footprints in stone across geological time. Other plumes have reshaped entire continents. The vast lava fields of India, known as the Deccan Traps, were created by a hotspot eruption so immense it may have contributed to the extinction of the dinosaurs. In Iceland, a hotspot rising beneath the mid-Atlantic ridge fuels constant volcanic activity, splitting the island in two even as new crust is born beneath it. These fiery anomalies remind us that the mantle is not uniform. It is a restless sea, dotted with rising plumes and sinking slabs, each one stirring the great pot of earth. The mantle also acts as a conveyor belt for crust. At mid-ocean ridges, molten rock wells up and hardens into new seafloor. This fresh crust is pushed outward, sliding away from the ridge as more material takes its place. At subduction zones, the conveyor turns downward, pulling old crust into the depths to be melted and recycled. The plates ride this cycle endlessly, created, carried, and destroyed by the currents below. It is a system that has run for billions of years, and without it, our planet would look nothing like it does today. Why, though, does this conveyor belt move so slowly? Plates drift at just a few centimeters a year, a pace almost comically sluggish. The answer lies in the sheer scale of the forces involved. The mantle is vast, and its currents operate on timescales far beyond our perception. The heat from the core rises steadily but not quickly, and the rocks of the mantle, though soft under pressure, are still resistant. It is as though an entire planet is caught in a slow-motion tug-of-war, with gravity, heat, and pressure all playing their part. Yet over time, those few centimeters add up. In a single human lifetime, a plate might shift only the width of your hand. But across 1,000,000 years, it moves tens of kilometers. Across hundreds of millions, oceans open, mountains rise, and continents drift from pole to pole. What feels to us like stillness is, to the Earth, a steady heartbeat, each pulse carrying the surface into a new arrangement. The deep engine is not uniform or predictable. Sometimes it speeds up, sometimes it slows. Slabs of cold crust sinking into the mantle can drag plates more quickly, while plumes of hot rock can force sudden bursts of volcanic activity. In some places, the mantle may even split into complex patterns of swirling flow, creating hotspots in unexpected locations. Though scientists have mapped much of the mantle using seismic waves, much remains mysterious. It is a hidden world, glimpsed only through vibrations and the clues left behind on the surface. There is something almost poetic about the way this engine works. Heat from Earth's fiery heart rises, cools, and sinks, creating a cycle that has no end. From this endless stirring comes the movement of continents, the birth of oceans, and the rise of mountains. The mantle is like the unseen breath of the planet, exhaled slowly through volcanoes, inhaled again as crust sinks back into the deep. For all its power, the deep engine is also fragile in its balance. Too much heat, and the crust would be torn apart too quickly. Too little, and the planet would stagnate, its surface frozen in silence. Our Earth exists in the sweet spot, restless enough to renew itself, steady enough to sustain life. It is this delicate balance that has allowed oceans to cycle, climates to shift, and life to flourish. When you stand on the ground and feel the illusion of stillness, remember that far beneath you, the mantle churns like an eternal tide. It pushes the continents together and pulls them apart. It builds mountains and opens seas. It is the unseen hand that writes the history of Earth, centimeter by centimeter, year by year, without pause or rest. The slow drift of plates may seem trivial compared to the speed of our daily lives, but without that drift, there would be no Himalayas, no Pacific Ring of Fire, no Atlantic Ocean stretching wide. The deep engine ensures that Earth is not a static sphere but a living, breathing world, and though it moves at the pace of eternity, its influence shapes every landscape, every coastline, and every horizon we see. The restless Earth begins in silence deep below, in the dark currents of the mantle. It is there that the story of drifting continents and shifting seas takes root, It is there that the patient heat of the core fuels the grand, slow dance of the plates. And it is there, hidden from sight, that the engine hums on, reminding us that stillness is never truly still. There are places on Earth where the planet is quietly tearing itself apart. They are not marked with flashing signs or warnings, and most lie hidden beneath the oceans, yet they are among the most important features of our restless world. These are the divergent boundaries, places where tectonic plates drift away from one another, pulling the crust apart and leaving space for new Earth to be born. It may sound dramatic, but it happens with such calm regularity that our entire planet has been reshaped by it, centimetre by centimetre, ridge by ridge, over hundreds of millions of years. The most famous example lies in the heart of the Atlantic Ocean, stretching like a vast scar from the icy north all the way down to the southern tip of the planet. The mid-Atlantic ridge is a mountain chain longer than anything on land. It winds across the seafloor for tens of thousands of kilometres, its peaks hidden beneath waves, its valleys home to creatures that thrive in total darkness. This ridge is no ordinary mountain range. It is a seam, a place where the Atlantic Ocean is opening wider with each passing year. Europe and Africa drift eastward, while the Americas slide away to the west, carried on plates that creep apart at the speed of a fingernail's growth. What makes this ridge remarkable is the process at its heart. Beneath it, molten rock from the mantle rises to fill the gap left by the separating plates. When this molten material cools, it hardens into new crust. In this way, the seafloor is constantly renewed, pushed outward from the ridge like pages on a conveyor belt. The crust near the ridge is young and fresh, while that at the edges of the ocean is ancient, having drifted for hundreds of millions of years before finally meeting its end in a subduction zone. This birth of new crust is not just a geological curiosity, it is the engine that drives the widening of oceans. Without it, there would be no Atlantic as we know it. The land masses of the world would still be locked together in ancient configurations, with no open sea between them. The mid-Atlantic ridge is proof that Earth is never finished, that it is always remaking itself in stone and water. And the ridge is not alone. Similar divergent boundaries crisscross the seafloor in every ocean. The East Pacific Rise, the Indian Ocean Ridge, and countless smaller rifts all mark places where Earth splits open to create anew. Together they form a global network of seams, a hidden pattern beneath the waves. The total length of these ridges is greater than all the rivers on Earth combined, yet most of them are unseen, their presence revealed only by sonar maps and seismic activity. Life, too, has found a way to thrive in these places of rupture. Along the ridges, hydrothermal vents spew superheated water rich in minerals, creating alien ecosystems that survive without sunlight. Giant tube worms, blind shrimp, and strange bacteria gather around these black smokers, drawing energy not from the sun but from the chemical reactions of the deep. In a way, the tearing of the crust has given birth not only to new seafloor but also to entire communities of life, sustained by the hidden furnace of the mantle. While most divergent boundaries are concealed beneath oceans, one remarkable rift can be seen on land. In eastern Africa, a great crack is splitting the continent apart. The East African Rift stretches thousands of kilometers from the Red Sea down through Ethiopia, Kenya, Tanzania, and beyond. Here, the African plate is slowly being torn into two, with the smaller Somali plate drifting eastward. Lakes fill the low spots, volcanoes rise along the edges, and the land itself is pulled apart by forces so slow and steady that they can scarcely be felt from one human lifetime to the next. Yet the results are unmistakable. Lake Tanganyika, one of the deepest lakes in the world, lies in a rift valley created by this slow tearing. The Great Rift Valley of Kenya is another visible scar, marked by steep cliffs and fertile plains. Over millions of years, this rift will widen until seawater rushes in, and a new ocean is born. One day, the Horn of Africa may be an island, separated from the mainland by a stretch of sea where now there are only fields, villages, and wild savannas. To imagine such a transformation is to glimpse the patience of the planet, oceans opening not with a roar, but with a whisper stretched over millennia. These rifts remind us that continents are not eternal fixtures. They are as restless as the oceans, splitting, drifting, and recombining in endless cycles. The land we consider permanent is, in reality, just one chapter in a story that spans billions of years. Today's valleys and ridges are tomorrow's seas and mountains. The Earth writes its history not in ink but in the slow rearrangement of stone. There is a strange comfort in this process. Though rifts can create earthquakes and volcanoes, their larger story is one of renewal. Divergent boundaries ensure that the planet is never stagnant, that crust is recycled, and that the surface remains dynamic. They are the quiet architects of oceans, the unseen hand that reshapes the map of the world. If you stand on the edge of the East African rift, you can see the ground opening beneath your feet, though only if you know where to look. The cracks may be small, the shifts imperceptible, yet they tell of a continent in motion. If you could return in 10 million years, you would not find the same landscape. Instead, there would be waves crashing on a new shore, islands scattered across the horizon, and a continent forever changed. The idea that Earth is splitting itself apart may seem unsettling, but it is also profoundly beautiful. The crust is not breaking in anger but in creation, making room for what comes next. Divergent boundaries remind us that endings and beginnings are often the same thing, that the rupture of today is the birth of tomorrow. And though we may never witness the full transformation with our own eyes, we walk every day on a planet that is quietly, patiently making itself anew. If divergent boundaries are Earth's way of creating new crust, then subduction zones are its way of tidying up. Our planet is a master recycler, never allowing its surface to simply accumulate forever. Instead, the crust is drawn back into the depths, melted, reshaped, and eventually reborn. This process is called subduction, and it is one of the most dramatic, dangerous, and creative forces at work beneath our feet. Subduction begins when two plates meet head-on. Unlike the slow parting of a rift, this is a collision. One plate must yield, and in most cases it is the denser oceanic crust that dives beneath the lighter continental crust. The descent is not graceful. It is a plunge into the mantle, forming a long scar in the ocean floor known as a trench. These trenches are some of the deepest places on Earth, hidden chasms that make the tallest mountains look small by comparison. The Mariana Trench in the western Pacific sinks nearly 11 kilometers below the surface, so deep that Mount Everest would vanish beneath its waves with room to spare. As the oceanic plate slides downward, it does not disappear quietly. The friction between the sinking slab and the overlying plate generates enormous stress, which is released as earthquakes. Some of the world's most powerful quakes have originated in subduction zones. The devastating event in Japan in 2011, which triggered a massive tsunami, began with a subducting plate jerking beneath the Eurasian plate. In Chile, Alaska, and Indonesia, similar collisions have unleashed seismic energy felt across oceans. But subduction is not only about destruction. As the oceanic crust descends, it carries with it water and sediments from the seafloor. When these materials reach the mantle, they lower the melting point of the rock, creating pockets of magma. This molten rock rises through the crust, erupting at the surface as volcanoes. The result is a volcanic arc, a chain of fiery mountains that parallels the trench below. The Andes in South America, the Cascades in North America, and the volcanoes of Japan and Indonesia are all born of this process. Together, trenches and volcanic arcs are the signature of subduction. One marks the place where crust sinks, the other where it resurfaces in fire. In between, earthquakes ripple as the plates grind and strain. It is a cycle of removal and renewal, destruction and creation, a geological breathing that has shaped coastlines and mountain ranges for hundreds of millions of years. From a distance, this recycling might seem ruthless. Oceanic plates are born at mid-ocean ridges, live their lives drifting across the seafloor, and eventually meet their fate in a trench. They are pulled downward, transformed by heat and pressure, and melted into the mantle. But it is this very process that prevents Earth from becoming a static, lifeless sphere. By recycling old crust, subduction allows the surface to stay dynamic. Without it, oceans would simply grow larger and larger, continents would pile up without end, and the surface would lose the balance that makes it so alive. The story of subduction can also be traced in the rocks. Ancient volcanic arcs leave behind granite mountain ranges once the volcanoes themselves have eroded away. Traces of long-vanished oceanic plates can be found as thin slices of basalt embedded in mountain belts. These relics are geological fossils, evidence of oceans that closed and disappeared long before humans appeared. The Himalayas, though born of continental collision rather than classic subduction, contain remnants of an ancient ocean floor now lifted high into the sky. The Alps, too, are stitched with fragments of ocean crust, carried upward as plates collided and recycled. Even the chemistry of our atmosphere owes something to subduction. Volcanoes fueled by descending plates release gases into the air, including carbon dioxide and water vapor. Over time, this exchange between mantle and sky has played a role in regulating climate, influencing ice ages and warm periods. In this way, subduction is not just a local event but a planetary one, linking the deep Earth to the surface and even to the air we breathe. Yet despite all we know, subduction still holds mysteries. Scientists debate exactly how it begins. Does a plate simply get too heavy and sink of its own accord, or must an outside force shove it into the mantle first? And why do some regions host long-lived subduction zones while others remain quiet for eons? These questions remind us that the Earth, for all our study, keeps its secrets close. There is also something humbling about the timescales involved. A plate may take hundreds of millions of years to complete its journey from ridge to trench. The ocean floor beneath your feet today may one day vanish entirely, swallowed by the mantle and reborn somewhere else. In the grand scheme of geology, nothing is permanent. Land and sea trade places, mountains rise and crumble, and crust recycles endlessly in a cycle older than life itself. To stand near a subduction zone, if one could, would be to feel the tension of opposites. Beneath the ocean, a slab of crust slides silently downward, while above it, a line of volcanoes marks its fiery transformation. The ground shudders with earthquakes, the coastline warps and shifts, and new mountains slowly rise. It is a place where the hidden forces of the planet are laid bare, not in sight but in sound and movement, in the rumble of the Earth's voice. Subduction is Earth's way of keeping balance, of ensuring that creation and destruction remain in harmony. For every kilometre of new crust born at a mid-ocean ridge, another is consumed in a trench. The planet does not grow larger, nor does it shrink. It simply recycles endlessly. The skin of Earth is renewed in fire and folded back into the depths, as though the planet itself were breathing in and out, slowly, patiently, across the ages. When we look at a map and see the arcs of volcanoes tracing the Pacific Rim, or the deep trenches cutting along the ocean floor, we are seeing only the surface of this process. Beneath lies a world of motion and heat, a cycle that has been at work since the earliest days of the planet. It is a reminder that nothing, not even the ground itself, is permanent. The continents we walk upon are temporary travellers, carried on plates that will one day vanish, replaced by new land in new arrangements. The restless Earth is not careless in its recycling. It is purposeful. Old crust is taken in, broken down, and given back in new form. Mountains rise from ashes, islands emerge from the sea, and the surface is forever remade. Subduction is not an ending but a transformation, a reminder that even the deepest destruction is also a beginning. The Earth recycles itself endlessly, and in that cycle lies both its mystery and its enduring beauty. When two continents collide, the result is not gentle. It is not the quiet slipping of plates beneath oceans or the slow stretching of a rift. It is the meeting of equals, each refusing to yield, each too buoyant to sink into the mantle. And when continents lock horns, the Earth responds by crumpling and folding, thrusting the crust upward into vast chains of mountains. This process is known as orogeny, mountain building, and it is one of the most awe-inspiring consequences of plate tectonics. The most famous example towers over Asia, the Himalayas. These immense peaks are the direct product of a colossal collision that began about 50 million years ago, when the Indian plate slammed into the Eurasian plate. Before that encounter, India had been a separate island continent drifting northward across the Tethys Ocean. It moved quickly by geological standards, racing north at nearly 15 centimeters a year. Eventually the gap closed, the ocean disappeared, and the two continents met with unstoppable force. With neither plate able to subduct, the crust had only one option: it had to go up. The result was the birth of the Himalayas, a mountain range so vast it reshaped not only the land but the climate of the entire planet. Even today the collision continues. The Indian plate is still pushing into Asia, and the Himalayas still rise, growing a few millimeters taller each year. For climbers, this means the world's highest peaks, like Everest and K2, are not frozen monuments, but works in progress, slowly climbing toward the sky. For geologists, it is a reminder that mountains are not just remnants of ancient upheaval. They are active, living landscapes, caught in the grip of forces far greater than themselves. But orogeny is not limited to Asia. Across the globe, mountain chains tell the stories of past collisions. The Alps formed when the African plate nudged into Europe, folding up rocks and leaving behind a landscape of jagged peaks and valleys. The Appalachians, older and more worn, are the eroded remains of a collision that once rivaled the Himalayas, when North America and Africa joined in the supercontinent Pangaea. Though time has softened them into rolling hills, their rocks still whisper of a violent birth long ago. The mechanics of mountain building are varied, but the essence is the same. Immense pressure forces rocks to bend, fold, and fracture. Layers of sedimentary rock that once lay flat at the bottom of ancient seas are shoved skyward, tilted into improbable angles, or even stacked one on top of another in great sheets. Whole sections of crust may thrust forward like giant wrinkles on the skin of the earth. Over time, erosion shapes these new ranges, rivers cutting deep valleys, glaciers carving ridges, wind and rain smoothing sharp edges into gentler forms. But beneath that sculpting, the upward push continues, keeping mountains alive against the forces that try to wear them down. This balance between uplift and erosion is why mountains can endure for so long. The Himalayas rise as fast as rivers, and weather can wear them down. If the collision ceased, the peaks would eventually crumble, ground down to plains over tens of millions of years. But as long as plates continue to collide, the rise and fall remain in balance, and the mountains endure. In this way, the tallest ranges on Earth are both fragile and eternal, always changing, never finished. The collision of continents does more than build mountains. It reshapes climates, diverts rivers, and even influences life itself. The uplift of the Himalayas, for instance, altered wind patterns and monsoon cycles across Asia, creating fertile plains that became home to great civilizations. The erosion of young mountains supplies rivers with sediments, nourishing farmlands downstream. Even global carbon cycles are affected, as fresh rock exposed by uplift reacts with the atmosphere, slowly drawing down carbon dioxide and influencing Earth's long-term climate. Mountains are not just scenery. They are engines of planetary change. The collision of India and Asia is particularly powerful because of its scale. The Indian plate is still moving north, bulldozing its way into Eurasia, and the impact zone stretches thousands of kilometers. Earthquakes ripple through the region, sudden reminders that the collision is far from over. Entire cities sit atop the grinding fault lines created by this slow-motion crash. For the people who live in the shadow of the Himalayas, the mountains are both a source of wonder and a source of danger. Majestic yet restless neighbors that can shake the ground without warning. Yet even as they threaten, mountains inspire. They rise as symbols of endurance, their peaks touching the sky, their valleys sheltering life. Poets, mystics, and travelers have looked to them as places of mystery and transcendence. For climbers, they represent the ultimate challenge. For scientists, they are windows into deep time, their folded rocks preserving records of vanished oceans and ancient collisions. Each layer of stone is a page in Earth's history, tilted and lifted for all to see. It is curious to think that mountains, which seem so solid, are products of motion. They are monuments to movement, the outcome of continents drifting and colliding. Their grandeur is born not of stillness but of conflict, not of permanence but of ceaseless change. And though they may seem timeless to us, they too will fade. One day the Himalayas will erode, their peaks ground down into sediments carried to the sea, just as the once mighty Appalachians were worn into gentle ridges. But for now they rise, reminders that the ground beneath us is never still. Why do mountains keep rising even today? Because the forces that created them are ongoing. The plates continue to push, the crust continues to crumple, and the mantle below continues to drive the motion. Mountains are caught in a constant tug of war, uplift pulling upward, erosion dragging downward. For as long as the balance tips toward uplift, the peaks will climb higher, defying gravity in their patient ascent. The story of colliding continents is one of power, patience, and transformation. It is a story written in stone, visible in the jagged skylines of young ranges and the softened hills of old ones. It reminds us that the landscapes we cherish are not fixed backdrops but active creations, forged in slow battles beneath our feet. The Himalayas may tower as the greatest symbol of this process, but every mountain range has its own tale of collision and uplift, its own chapter in the restless history of Earth. When we gaze at the mountains, we are looking at the frozen moment of impact, the crust mid-crumple, the Earth caught in the act of reshaping itself. And as the sun sets on their peaks, glowing with colours that shift by the hour, it is worth remembering that they are still rising, still changing, still writing their story in stone. Mountains are not simply there, they are becoming, and in their becoming lies the wonder of a planet forever in motion. For most of the time, the ground beneath us is steady, reliable, a surface we rarely question. But every so often, it reminds us that it is alive with motion. An earthquake is the sudden release of tension built up over years, decades, or even centuries, a jolt of energy that ripples through the crust. It arrives without ceremony, shaking cities, toppling buildings, and shifting landscapes in moments. These sudden quakes are the most immediate reminder that Earth is restless, and that the calm under our feet is only an illusion. The story begins with faults, those invisible cracks where tectonic plates grind against one another. Plates do not slide smoothly like well-oiled gears. Their edges are rough, jagged, and stubborn. As they try to move, friction holds them in place, locking the rocks together, but the mantle continues to push, forcing the plates onward. Stress builds, slowly bending and straining the crust until it can no longer resist. Then, in a fraction of a second, the rocks slip, and all that pent-up energy is released. The result is an earthquake, the ground trembling as seismic waves race outward. These waves travel in different ways. Primary waves, or P waves, move quickly, compressing and expanding the ground like a spring. Secondary waves, or S waves, follow, shaking the earth side to side. Finally, surface waves roll along the top of the crust, causing the most visible destruction. To someone standing above, it can feel as though the ground itself has turned to liquid, rippling beneath their feet. In truth, it is solid rock transmitting energy at astonishing speeds. Throughout history, earthquakes have left their mark on human lives. The city of Lisbon was struck in 1755 by one of the most powerful quakes in European history, followed by a devastating tsunami and fires. It shook not just the land, but the cultural and philosophical foundations of Europe, inspiring debates about science, religion, and the nature of disaster. In 1906, San Francisco was torn apart when the San Andreas Fault lurched forward, toppling buildings and igniting fires that consumed much of the city. In 2011, Japan faced a magnitude 9 earthquake that unleashed a towering tsunami and triggered the Fukushima nuclear crisis, a reminder of how even the most technologically advanced societies remain vulnerable. These events may feel like rare accidents, but earthquakes occur constantly. Thousands happen every day around the world, most too small to feel. Sensitive instruments called seismographs record them, tracing the pulse of Earth's crust with delicate precision. Only the largest quakes capture human attention, but together they reveal a planet that is always moving, always straining against itself. Humans living on this restless surface have long tried to predict and prepare for these jolts. Ancient cultures explained earthquakes through myth. Giants shifting in their sleep, gods shaking the land in anger, or animals beneath the earth tossing and turning. Today, scientists know the mechanics, yet prediction remains elusive. Faults do not keep tidy schedules. Stress can build for decades and release suddenly, or it can creep in small slips that avoid major quakes altogether. Seismologists can identify regions at risk, but they cannot yet say when or where the next big one will strike. Preparation, then, becomes the key. Modern cities in earthquake-prone zones design buildings to flex and sway rather than snap. Bridges and skyscrapers are fitted with shock absorbers and deep foundations. Early warning systems now exist in some countries, using networks of sensors to detect the first, faster P waves and send alerts before the more destructive waves arrive. In Japan, this can give people a few precious seconds to seek shelter or halt trains. It is not much, but even a brief warning can save lives. Still, the unpredictability of earthquakes keeps them among the most feared natural hazards. Volcanoes rumble and give warning, hurricanes can be tracked as they form, but earthquakes strike with little notice. This suddenness is part of what makes them so powerful, not only in physical destruction, but in the human imagination. They remind us that we are not the masters of the ground we build upon, but passengers riding a shifting crust. Yet there is more to earthquakes than destruction. They also play a role in shaping landscapes. Faults uplift mountains, create valleys, and even alter rivers. Some lakes exist only because earthquakes warped the land into new basins. Over long timescales, the jolts that terrify us contribute to the planet's beauty. They are part of the cycle of renewal, the violent punctuation marks in Earth's ongoing story. One curious effect of earthquakes is their ability to travel across vast distances. Seismic waves from a major quake can circle the globe multiple times, recorded by instruments on the far side of the world. It is as though the entire planet vibrates in sympathy, ringing like a struck bell. For geologists, these vibrations are invaluable. By studying how seismic waves move through the Earth, scientists can peer into the planet's interior, mapping the mantle and even the core. In this way, earthquakes act as natural probes, revealing the hidden structure of the world beneath us. In quieter moments, one might even find something humbling in earthquakes. They are proof that the Earth is alive, dynamic, unwilling to be tamed. We build cities, carve roads, and raise monuments. Yet a sudden shift deep below can remind us how fragile our works are. This is not cause for despair, but for perspective. The planet has been quaking for billions of years and will continue long after us. To live here is to share space with a restless companion, to build with respect for the motion beneath. The sudden jolt of an earthquake is both terrifying and fascinating. It can topple towers and erase coastlines, yet it also teaches, shaping our understanding of geology and forcing us to adapt. It is the price and privilege of living on a planet that is still active, still evolving, still restless at its core. The ground may seem solid, but it is only temporarily so. Somewhere, stress is building, waiting for the moment it will be released in a tremor that rattles our world once more. There are places on Earth where the planet quite literally breathes fire. Volcanoes are the visible outlets of Earth's deep engine, vents through which molten rock, gas and ash escape to the surface. They are both feared and revered, symbols of destruction and renewal. To watch one erupt is to witness the Earth in its most dramatic performance, a reminder that beneath our feet lies a world of heat and pressure always seeking release. The greatest stage for this fiery drama is the Pacific Ring of Fire. Stretching around the edges of the Pacific Ocean like a necklace of flame, it is home to more than 3/4 of the world's active volcanoes. From the Andes in South America to the Cascades in North America, across to Japan, the Philippines, and down into New Zealand, this ring is where tectonic plates converge and subduction zones run deep. Here, oceanic crust plunges into the mantle, melts, and fuels chains of volcanoes that line coastlines and island arcs. The Ring of Fire is restless, alive with eruptions, earthquakes, and the constant reminder that the Pacific Plate is the largest but also one of the most beleaguered players in Earth's tectonic puzzle. Not all volcanoes, however, are the same. Some rise as gentle giants, spreading their lava in broad flows that build wide, low profiles. These are shield volcanoes, named for their resemblance to a warrior's shield lying on the ground. Their eruptions tend to be relatively calm, releasing rivers of basaltic lava that can travel great distances before cooling. The Hawaiian Islands are the classic example, with Mauna Loa and Kilauea quietly reshaping the landscape over and over. To stand on their slopes is to feel the patient power of a volcano that builds land not with explosions, but with steady outpourings of molten rock. Other volcanoes, however, are far less gentle. Stratovolcanoes, also known as composite volcanoes, rise as steep, towering cones built from alternating layers of lava, ash and debris. Their eruptions can be catastrophic, driven by thick magma that traps gas until pressure reaches unbearable levels. When they blow, the results can be devastating. Mount Vesuvius buried Pompeii in a storm of ash in 79 CE, freezing an entire city in time. Krakatoa erupted in 1883 with such force that it shattered the island and sent tsunamis racing across the Indian Ocean, its sound heard thousands of kilometers away. More recently, Mount St. Helens in 1980 tore off the side of its own summit in a lateral blast that flattened forests and darkened skies. Stratovolcanoes are dangerous precisely because they can appear quiet for centuries, only to awaken with fury that alters landscapes overnight. Despite their dangers, volcanoes are not only destroyers, they are creators of land. Much of the world's surface owes its existence to volcanic activity. Islands like Hawaii, Iceland and the Galapagos were born from eruptions that built them up from the seafloor. The very crust beneath our oceans is made of lava that once welled up at ridges. Even continents bear scars of ancient volcanic provinces where massive outpourings of lava once reshaped entire regions. Over time, weather and erosion transform volcanic rock into fertile soils, rich in minerals that sustain life. Some of the world's most productive farmlands lie on volcanic slopes, where crops thrive in soils born of fire. Volcanoes also play a surprising role in shaping climate. When they erupt, they release not just lava and ash but gases, particularly carbon dioxide and sulfur dioxide. Over long timescales, this steady outgassing has helped regulate Earth's atmosphere, balancing carbon between the mantle, oceans and sky. In short bursts, however, volcanic eruptions can cause dramatic shifts. The eruption of Mount Tambora in 1815 released so much ash and gas into the atmosphere that it dimmed sunlight worldwide, leading to what became known as the year without a summer. Crops failed, temperatures dropped, and people as far away as Europe and North America felt the chill of a volcano on the other side of the world. The dual nature of volcanoes, as both creators and destroyers, has given them a special place in human imagination. Myths and legends often describe them as the dwelling places of gods or spirits. Cultures living near active volcanoes developed stories to explain their behavior, from Pele, the fiery goddess of Hawaiian lore, to Japanese tales of Mount Fuji's divine presence. Even today, volcanoes inspire both awe and respect. People build cities in their shadows, drawn by fertile soils and strategic locations despite the risks. The knowledge that fire may one day return is balanced by the gifts volcanoes provide. Scientifically, volcanoes are also windows into Earth's interior. When magma erupts, it carries with it minerals and gases from deep within the mantle, clues to processes we cannot otherwise see. By studying volcanic rocks, scientists learn about the composition of Earth's interior, the cycling of elements, and the forces driving tectonic motion. In a way, volcanoes are the planet's storytellers, speaking in lava and ash of things hidden far below. To stand at the edge of an active volcano is to confront Earth's raw power. The ground trembles, gases hiss from vents, and molten rock glows with an intensity that seems almost alive. Yet there is also beauty in this danger. New land forming, islands rising from the sea, night skies lit by fountains of lava. Volcanoes are a reminder that creation often comes hand in hand with destruction, that renewal requires change, and that the surface we live upon is never truly finished. Around the Ring of Fire, from Alaska to Chile to Japan, this cycle continues. Shield volcanoes spread their gentle flows, stratovolcanoes bide their time until their next eruption, and countless submarine volcanoes bubble quietly beneath the waves. Together they shape coastlines, feed ecosystems, and influence climates. They are not accidents of geology, but essential components of Earth's living system, recycling material, releasing gases, and building the very land we stand on. The restless Earth expresses itself most vividly through volcanoes. They are the planet's breath made visible, fire from below that both threatens and sustains. They connect the deep mantle to the surface, the unseen to the seen, the hidden engine to the world we know. And as long as the Earth's core remains hot, as long as plates move and mantle plumes rise, volcanoes will continue to erupt, sometimes quietly, sometimes explosively, but always as part of the great rhythm of a planet that never truly rests. Beneath the waves lies a world as vast and mysterious as outer space. The ocean floor, hidden beneath kilometers of water, is not a flat and featureless plain, but a landscape of mountains, valleys and chasms more dramatic than anything on land. It is a realm where the restless movements of tectonic plates are written into stone, where fire and water meet, and where life has found ways to flourish in the most unlikely of places. Most of the seafloor is made up of abyssal plains, wide stretches of flat terrain that cover much of the deep ocean. They may seem monotonous, but they are among the smoothest, most extensive surfaces on the planet. These plains are blanketed with fine sediments that drift down over millions of years, burying older features and creating a quiet, level floor. Yet even here, the serenity is deceptive. Beneath the layers of sediment lies oceanic crust that is constantly moving, born at ridges and destined one day to be consumed in trenches. The abyssal plains are the calm surface of an active conveyor belt, a reminder that even the stillest landscapes are caught in motion. In other parts of the ocean, the seafloor plunges into extraordinary depths. Subduction zones carve trenches that are the deepest scars on Earth. The Mariana Trench in the Western Pacific is the most famous, dropping almost 11 kilometers into the dark, a depth so extreme that only a handful of humans have ever visited. Trenches are places of immense pressure, where slabs of crust vanish into the mantle, dragging sediments, seawater, and even bits of the biosphere down with them. They are the planet's great recycling bins, places where the skin of Earth is swallowed whole, only to be reborn elsewhere. Balancing these abysses are the mid-ocean ridges, immense mountain chains that run through every ocean like seams on a baseball. Together they form the longest mountain system on Earth, stretching more than 60,000 kilometers. At these ridges, tectonic plates pull apart and molten rock rises to create new crust. Though hidden beneath the sea, they are landscapes of fire, with lava erupting in darkness and fresh crust spreading outward to build the ocean floor. If the oceans were drained, these ridges would be the most striking features on the planet, greater in scale than even the Himalayas. One of the most extraordinary discoveries of the last century came from studying these ridges. In the late 1970s, scientists exploring the Galapagos Rift stumbled upon hydrothermal vents, towering chimneys belching superheated water rich with minerals. To their astonishment, they also found thriving ecosystems clustered around these vents, creatures that lived without sunlight, sustained by bacteria that drew energy not from photosynthesis, but from chemical reactions with the vent fluids. Here were giant tube worms, clams, and crabs living in the darkness, proving that life could flourish in conditions once thought impossible. These vent communities changed our understanding of biology. They showed that sunlight is not the only source of energy for life, that chemistry itself can provide the spark for ecosystems. Some scientists even speculate that early life on Earth may have originated in environments like these, nurtured by mineral-rich waters and protected from the chaos of the young planet's surface. Today, hydrothermal vents remain places of wonder. Their surreal creatures a reminder that life is resourceful, able to adapt to the most extreme conditions. The seafloor also preserves a record of Earth's restless history. As new crust forms at ridges and spreads outward, it carries with it magnetic fingerprints. When lava cools, the iron within it aligns with Earth's magnetic field. Over time, the planet's magnetic poles have flipped many times, and each reversal is frozen into the rocks as stripes of opposite polarity. These magnetic patterns, mirrored on either side of ridges, provide a timeline of seafloor spreading, proof of how oceans grow and change. Sediments too hold clues. Layers of microscopic shells rain down from the surface, accumulating year by year, recording shifts in climate and ocean chemistry. By studying these deposits, scientists can reconstruct ancient climates, tracing ice ages, warm periods, and mass extinctions. In a way, the ocean floor is Earth's archive, a library of stone and sediment that preserves the memory of deep time. And yet, despite all these discoveries, the ocean floor remains largely unexplored. More people have walked on the surface of the moon than have visited the deepest trenches of Earth. Sonar has mapped large-scale features, but vast areas remain only roughly charted. The deep ocean is still a frontier, a realm of mystery where new species and unexpected geological phenomena are waiting to be found. Every expedition into the depths reveals something surprising, a new vent field, a strange creature, a landscape no one imagined. There is something humbling about knowing that such an immense part of our own planet remains hidden. The ocean floor is not just scenery, it is the stage on which the drama of plate tectonics plays out most vividly. It is where new crust is born, where old crust is destroyed, and where the restless cycle of Earth's surface is most clearly written. To explore it is to peer into the very machinery of the planet, to watch the gears of geology turning in darkness. When you think of the seafloor, imagine not emptiness, but a living, shifting world. Picture the abyssal plains, vast and quiet, lying above crust that is drifting toward its fate. Picture the trenches, deep and foreboding, swallowing the skin of the earth. Picture the ridges, fiery seams where new land is born, and the vents, glowing oases of life in a black ocean. And picture, too, the hidden record of time, written in stone and sediment, waiting patiently for us to read it. The hidden ocean floors are proof that the Earth is not a finished world, but a work in progress. They are where geology continues to write the planet's story, where creation and destruction unfold unseen, and where life finds ways to thrive in the most unlikely places. Beneath the waves lies a planet within a planet, a reminder that the ground we know is only part of the story, and that the greatest landscapes may be those we have yet to fully see. The continents may look like they have always belonged where they are now, but their arrangement is only a snapshot in a much longer story. Over billions of years, the land masses of Earth have wandered across the globe, colliding and breaking apart in a grand cycle known as the supercontinent cycle. Continents are not fixed pieces on a board, but restless travelers, pulled together by tectonic forces only to be scattered again. This cycle has repeated itself many times, reshaping the face of the planet and influencing everything from climate to the course of evolution. One of the most famous supercontinents is Pangaea, a vast landmass that formed about 300 million years ago. Its name means all Earth, and it lived up to its title. Nearly all the continents we know today were fused into one colossal expanse, stretching from pole to pole. The interior of Pangaea was likely dry and harsh, far from the moderating influence of the ocean. Deserts stretched across its heart, while coasts teemed with life. Pangaea was home to early reptiles, giant amphibians, and the ancestors of dinosaurs. It was a world united by land, yet its very size created climates and ecosystems unlike anything we know today. But Pangaea was not the first. Before it, there was Gondwana, which began assembling more than 500 million years ago. Gondwana brought together what is now South America, Africa, Antarctica, Australia, and the Indian subcontinent. It dominated the southern hemisphere, its breakup later sending fragments drifting northward to join other continents. And before Gondwana, there was an even older configuration called Rodinia, dating back more than 1 billion years, long before complex life filled the seas. Each supercontinent has its moment in the planet's story, a fleeting arrangement in the slow dance of tectonic plates. Pangaea eventually split apart, just as its predecessors had. Around 200 million years ago, rifts opened, and the land began to tear into pieces. The Atlantic Ocean slowly widened, separating the Americas from Europe and Africa. India drifted north, colliding with Asia to raise the Himalayas. Australia slipped free of Antarctica and wandered into the Pacific. The world map began to resemble something closer to the one we know today, though the continents are still moving even now. This breakup was not random. It was driven by the same forces that built Pangaea in the first place: mantle convection, subduction, and rifting. Plates collide to form supercontinents, but heat trapped beneath such vast landmasses eventually pushes upward, splitting them apart. The process is like a cosmic heartbeat, continents coming together, drifting away, and then reuniting in new configurations. Geologists believe this rhythm is repeated at least 3 times, perhaps more, each cycle spanning hundreds of millions of years. The supercontinent cycle has left deep marks on Earth's history. When continents gather, sea levels often fall, exposing wide stretches of land and altering ocean circulation. When they break apart, shallow seas form along rifted coasts, creating habitats that can spark evolutionary booms. Climate too is reshaped. A giant supercontinent may disrupt global wind patterns, while its breakup can spread landmasses into new latitudes, altering rainfall, temperature, and ocean currents. Even mass extinctions have been linked to these shifts, as ecosystems struggle to adapt to the changing stage. The cycle is not finished. Just as Pangaea split, today's continents will one day collide again. Scientists have speculated about the shape of the next supercontinent, often called Pangaea Ultima. If current plate motions continue, the Atlantic Ocean will eventually close, bringing the Americas back into contact with Europe and Africa. Meanwhile, Africa will continue moving northward, colliding fully with Europe to raise new mountains where the Mediterranean Sea once lay. Australia may drift further north to join Asia, while Antarctica might move into warmer latitudes. The result would be another colossal landmass, ringed by a vast global ocean. The timescale for such a union is immense, hundreds of millions of years. Humanity will not be here to witness it, but the cycle will continue regardless. To think of Pangaea Ultima is to imagine a future Earth utterly transformed, where familiar coastlines vanish and deserts stretch where oceans once lay. It is a reminder that even the map we take for granted is temporary, one more moment in a restless story. The supercontinent cycle is perhaps one of the most humbling aspects of geology. It shows us that permanence is an illusion, that the very ground beneath us is temporary. Mountains rise and fall, oceans open and close, and continents wander like slow, stubborn travelers across a vast and shifting stage. The names may change, Rodinia, Gondwana, Pangaea, Pangaea Ultima, but the rhythm remains the same. There is something strangely comforting in this repetition. The Earth remakes itself not in chaos but in cycles, patterns that endure across billions of years. The continents may wander, but their journeys follow a rhythm as steady as a heartbeat, as ancient as the planet itself. To look at a map today is to glimpse only one chapter, a fleeting arrangement of land and sea in a story that began long before us and will continue long after. The continents do not ask for permission, nor do they wait for us to notice. They drift, collide, and part again, shaping the world anew. And though we may never see the rise of Pangaea Ultima with our own eyes, the knowledge that it will come reminds us that the Earth is not finished. It is a planet forever in motion, forever rearranging, forever restless in its dance across the ages. The restless motions of Earth's plates are not only sculptors of mountains and makers of oceans, they are also quiet architects of climate and life. Though their movements are slow, the consequences ripple across millions of years, shaping the carbon cycles that govern the air we breathe, the ice ages that advance and retreat, and the very patterns of evolution that fill the planet with living diversity. Plate tectonics is more than geology. It is an unseen guide to the history of life itself. At the heart of this connection lies the carbon cycle. Carbon is the currency of life and climate, traded constantly between atmosphere, oceans, rocks, and living things. Volcanoes, fueled by subduction and mantle plumes, are one of the main sources of carbon dioxide released into the air. Every eruption, every vent, every steady exhalation from the deep mantle adds to the atmosphere, warming the planet and feeding photosynthesis. But tectonics also provides the counterbalance. When mountains rise, their exposed rocks weather under the assault of rain and wind. This weathering draws carbon dioxide from the air, locking it into minerals and carrying it back to the oceans, where it eventually sinks into the crust. Subduction then drags this carbon-rich crust back into the mantle, completing a cycle that has run for billions of years. This long-term balance is why Earth has remained habitable for so long. Without tectonics, carbon dioxide would either build up endlessly, turning the planet into a greenhouse like Venus, or be trapped forever in rocks, leaving Earth frozen like Mars. Instead, the ceaseless motion of plates keeps the system in check, ensuring that carbon is recycled, released, and withdrawn in a rhythm that allows life to flourish. It is a thermostat written in stone, adjusted not by human hands but by the deep breath of the planet. The drifting of continents has also steered the course of ice ages. When land masses gather at the poles, ice sheets can expand, reflecting sunlight and cooling the planet further. When continents cluster near the equator, the climate tends to be warmer as dark oceans absorb heat. Around 34 million years ago, Antarctica drifted into its present position, encircled by a new current in the Southern Ocean. This isolation trapped cold around the continent, leading to the spread of massive ice sheets that still dominate today. Later, the uplift of the Himalayas, born from the collision of India and Asia, increased global weathering, drawing down carbon dioxide and tipping Earth into a cooler climate. These shifts remind us that the slow movements of plates, imperceptible in a human lifetime, can set the stage for planetary transformations. The ice ages of the last few million years, which shaped the landscapes we know today, owe part of their existence to tectonic rearrangements that altered ocean currents and atmospheric balances long before humans appeared. Glaciers advancing and retreating across continents, carving valleys and leaving behind fertile soils, were in many ways the echoes of continents shifting on their ancient journey. Biodiversity too has been shaped by drifting continents. When land masses merge into supercontinents like Pangaea, ecosystems mingle, species compete, and some are driven to extinction. When continents break apart, populations are isolated, and evolution takes new, divergent paths. Australia, set adrift from Gondwana, became a cradle for marsupials and monotremes found nowhere else. South America, long isolated, nurtured its own unique fauna until the rise of the Isthmus of Panama connected it to North America, triggering a great exchange of species. Africa's slow northward drift exposed its rift valleys and savannas, shaping the environments where early humans evolved. Even the great evolutionary radiations of marine life are tied to tectonics. The opening and closing of seaways redirect ocean currents, stirring nutrient cycles and changing habitats. When the Atlantic widened, it created new coastlines and shallow seas, inviting bursts of diversity. When the Tethys Ocean vanished beneath the advancing Indian Plate, whole ecosystems were erased, while new ones appeared in the rising Himalayas. Life follows the script of plate tectonics, adapting to the landscapes and climates that drifting continents provide. To think of tectonics as life's hidden guide is to recognize how much of biology is written in geology. The forests that spread across continents, the deserts that form in their interiors, the savannas where humans first walked upright, all were shaped by the motion of plates. Even today, the climate zones we live in, the currents that carry rainfall and the soils that feed our crops are gifts of tectonic restlessness. Without moving plates, Earth might be a barren sphere, a planet with oceans and rocks but no rich story of evolving life. What makes this story all the more remarkable is its timescale. The plates drift only a few centimeters a year, but in their patience lies power. Over millions of years, these small shifts accumulate into profound transformations. A continent nudges north, and an ice sheet spreads. A mountain range rises, and global carbon dioxide falls. An ocean opens, and new species burst into existence. The slow heartbeat of tectonics echoes in every glacier, every forest, every coral reef. There is a gentle irony in this. Earthquakes and eruptions grab our attention because they are sudden, but it is the slow drift of plates that has shaped the grand history of life. The hidden forces of tectonics are like a quiet hand, guiding the course of climate and biodiversity in ways we often overlook. They are not dramatic in the moment, but they are decisive in the long run. When we look at the natural world around us, it is easy to see life as separate from geology. Trees grow, animals roam, clouds gather, and rivers flow. Yet beneath it all, the stage itself is shifting, and with it the rules of the play. Life has always danced to the rhythm of drifting continents and colliding plates. Our very existence is tied to mountains rising, oceans opening, and carbon cycles whispering between sky and stone. Plate tectonics is the quiet partner of evolution, the unseen architect of climate, the hidden guide of life. It reminds us that Earth is not a static home but a living, moving world, where the slowest motions create the deepest impacts. And as the continents continue their journeys, they will keep shaping the climate, reshaping ecosystems and guiding the story of life in ways we cannot yet imagine. The restless Earth is not only beneath our feet, it is within the very air we breathe and the lives we lead. The rocks beneath our feet are not just stone, they are archives, holding stories written long before humans could record history. Among the most vivid of these tales are fossils, the imprints and remains of creatures and plants that once thrived in ancient worlds. Fossils do not simply tell us about life, they also tell us about the land itself. When identical fossils appear on continents now separated by oceans, they reveal that the continents were once joined, sharing climates, ecosystems, and creatures that wandered freely across their united landscapes. One of the most persuasive examples comes from a small reptile called Mesosaurus. This creature lived more than 250 million years ago, a freshwater dweller only about a meter long. Its fossils have been found in both South America and Southern Africa, but nowhere else. Freshwater reptiles are not exactly known for crossing oceans, so the logical conclusion is that these continents were once connected. At the time of Mesosaurus, South America and Africa were neighbours, joined in the supercontinent Gondwana. Only later did the Atlantic Ocean split them apart, leaving the fossils stranded on opposite shores. Another clue lies in the plant Glossopteris, a fern-like tree that flourished across Gondwana. Its fossils are found in India, Africa, South America, Antarctica, and Australia. Today, these continents are scattered far apart, separated by vast oceans and climates ranging from tropical to frozen. Yet the spread of Glossopteris fossils shows that these lands were once joined in a single, continuous range where the plant thrived. The distribution of this ancient flora is like a green fingerprint pressed across the continents, evidence of their shared past. Dinosaurs too leave behind migration stories told in stone. Fossils of similar species appear on continents that are now distant neighbours. For example, fossils of the carnivorous dinosaur Allosaurus in North America share striking similarities with related species in Africa and Europe, suggesting land connections in the Jurassic period. Sauropods, those long-necked giants, left their tracks across South America, Africa and India, walking across landscapes that would later be torn apart by tectonic rifting. Their presence in multiple regions is not coincidence. It is testimony to a world where continents had not yet drifted to their current positions. The story extends even further back, into forests that once stretched across now separate continents. Coal deposits in North America and Europe contain fossilized remains of swamp forests from the Carboniferous period, when those lands lay close together near the equator. Similar deposits are found in China and Siberia, linking distant regions into a single belt of lush, humid greenery. The spread of these ancient forests is a map not of today's world, but of a world long gone, when continents were arranged in patterns that only fossils now reveal. Some of the most striking fossil evidence comes from Antarctica, a land we imagine as lifeless ice. Beneath its glaciers lie fossils of temperate forests, complete with tree stumps, leaves and pollen. There are also fossils of reptiles that lived in warm conditions, far from the frozen world we see today. These discoveries only make sense when we realize that Antarctica was once part of Gondwana, connected to South America, Africa and Australia, and positioned closer to the equator. The icy desert of today was once a green, vibrant land, home to forests and creatures that vanished when tectonics carried the continent into colder latitudes. Fossils also reveal the migration stories of smaller, less famous creatures. Tiny marsupial fossils connect South America to Antarctica and Australia, tracing their journey before the continents drifted apart. Fossilized freshwater amphibians, unable to cross saltwater seas, appear on multiple continents, further evidence of ancient connections. Even the microscopic remains of plankton, preserved in layers of sediment, provide clues to the movement of oceans and continents over time. Each fossil, no matter how small, is a thread in the larger tapestry of Earth's shifting surface. These discoveries were crucial in supporting the theory of continental drift. When Alfred Wegener first proposed the idea, he pointed to fossils as one of his strongest lines of evidence. The puzzle piece fit of South America and Africa was compelling, but it was the identical fossils of plants and animals across oceans that made the argument hard to dismiss. Critics could deny the visual fit of the continents, but they could not explain how a freshwater reptile had managed to swim across the Atlantic, or why the same fern grew in both India and Antarctica. Fossils carried the truth of tectonics in their silent testimony. Beyond proving that continents move, fossils remind us of the dynamic link between life and geology. The drifting of continents did not just scatter fossils, it scattered ecosystems, split populations, and forced evolution down new paths. When land masses split, species were isolated and adapted to their new environments. When continents collided, animals and plants mixed in waves of migration. The fossil record captures these turning points, moments when geology reshaped the stage and life responded in kind. In this way, fossils are not static relics, but storytellers. They speak of lush forests now buried under deserts, of animals that walked across lands long since torn apart, of climates that changed as continents drifted across latitudes. They show us that the Earth we know is temporary, that the arrangement of land and sea is fleeting, and that life has always been carried along by the planet's restless motions. There is also something deeply human in the way we read these stones. To hold a fossil is to touch a moment in time, a leaf that fell or a footprint pressed millions of years ago. When that fossil is found on one continent and its twin on another, it is like piecing together a puzzle across oceans. It is proof that the planet itself moves, and that life leaves its mark not only in living descendants, but in the silent rocks beneath us. The continents have always been in motion, but fossils are their breadcrumbs, scattered trails left behind for us to follow. They connect Africa to South America, India to Antarctica, North America to Europe, and in doing so they connect us to the long hidden journey of the Earth. They remind us that the map we know is not fixed but fluid, and that beneath every stone lies the possibility of another story, waiting to be uncovered. Far out in the world's oceans, away from the noise of continents colliding, lie strings of islands that tell their own quiet story of Earth's restlessness. These islands do not form at the edges of plates where subduction creates fiery arcs. Instead, they rise from the deep blue at places called hotspots, localized plumes of heat that pierce the crust from far below. When a tectonic plate drifts over a hotspot, volcanoes bloom one after another, leaving behind trails of islands that act like time markers, recording the steady movement of the plate above. The Hawaiian Islands are the most famous of these. Stretching across the central Pacific, they are a living laboratory of hotspot geology. The Big Island of Hawaii, youngest of the chain, still hosts active volcanoes, with molten lava spilling into the sea and building new land with each eruption. To the northwest, Maui, Oahu, and Kauai stand as older siblings, their volcanoes long extinct, their slopes softened by erosion, their peaks cloaked in greenery. Further still lies the Emperor Seamount Chain, a string of submerged volcanoes that trace the Pacific Plate's path back for more than 80 million years. Each island and seamount is a footprint of the plate's journey across a single stationary plume of heat. This trail is more than scenic. It is geological proof of plate motion, a dotted line drawn across the ocean floor that records millions of years of drift. The Hawaiian Emperor Chain even reveals a dramatic change in direction, a bend that occurred about 50 million years ago when the Pacific Plate altered its course. That kink in the line is not just a curiosity, it is a timestamp of Earth's shifting motions, a frozen record of when the entire plate reorganized itself. Hotspot islands are not limited to Hawaii. Iceland sits atop a hotspot where it meets the mid-Atlantic ridge, a rare combination that fuels constant volcanic activity. The Galapagos Islands in the eastern Pacific owe their origins to a hotspot, as do the Canary Islands in the Atlantic and Reunion in the Indian Ocean. Each chain has its own personality, shaped by the interplay of plume, plate, and ocean. Some are lush with life, others stark and volcanic, but all share the same quiet origin, a stationary source of fire beneath a moving crust. Volcanic island arcs, meanwhile, form in a different way, though they too trace the story of tectonic restlessness. Unlike hotspot chains, arcs arise above subduction zones, where oceanic plates sink beneath one another. As the descending slab melts, magma rises and erupts to form a curved line of islands. The Aleutian Islands of Alaska, the Mariana Islands of the Western Pacific, and the Lesser Antilles of the Caribbean are all arcs born of subduction. These arcs mirror the trenches below, curving across oceans like delicate threads. They are built by collisions, yet they carry the same sense of patient beauty as hotspot islands. Volcanoes rising from the sea, shaped by forces hidden from view. Island arcs have played an important role in Earth's history. They are stepping stones across oceans, routes for migration of species, and even seeds for continents themselves. When arcs collide with larger landmasses, they can weld onto them, adding new crust and expanding continents bit by bit. Over billions of years, arcs may have been crucial in building the continents we know today, stitching together fragments into larger bodies of land. The beauty of islands, whether hotspot chains or volcanic arcs, lies in their dual nature. They are born from violence, eruptions, lava flows, and fiery plumes, but they settle into havens of life. Hawaii's slopes are covered in rainforests, waterfalls, and coral reefs, nurtured by volcanic soils rich in minerals. Iceland's stark lava fields support mosses and birds that thrive in the cool North Atlantic. Even the barren, windswept islands of arcs become home to seabirds, plants, and human communities, all finding a way to live on land that did not exist only a few million years before. These islands also remind us of scale. To us they feel permanent, fixed places on the map. But to the Earth, they are fleeting. Hotspot islands slowly sink as the crust beneath them cools and subsides. Waves erode their shores, winds wear down their peaks, and in time they vanish beneath the sea, becoming seamounts like those that trail behind Hawaii. Arcs, too, are temporary, shifting as subduction zones migrate and trenches shift. The islands we know today are only chapters in a longer story, their beauty caught in a moment between creation and disappearance. There is a quiet poetry in how these islands chart the motion of the plates. A hotspot chain is like a dotted line written across the ocean, spelling out the story of drift. An arc is like a stitched seam, binding together pieces of crust into larger holes. Both speak of movement that is invisible to us in the present but undeniable when traced over millions of years. They are the punctuation marks of tectonics, small but eloquent reminders that the Earth never stands still. To stand on a volcanic island is to feel close to the heart of the planet. Beneath your feet lies rock that was once molten, lifted from deep within the mantle and poured out into the open air. The very ground is new, born from fire and cooled into solidity within a span of time that is short by geological standards. Look to the horizon, and you may see older siblings in the chain, their peaks softened, their volcanoes long dead. Look further still, and beyond the waves lies the unseen trail of seamounts, marching back into the past. Islands in the stream are reminders that Earth's creativity is patient. They appear in the middle of vast oceans, remote and improbable, yet they are inevitable products of the planet's restlessness. They are markers of time, of drift, of fire meeting water, and of land emerging where none existed before. Whether lush with life or stark and volcanic, they are chapters in the grand narrative of geology, each one a fleeting stop on the journey of the plates. And as the plates continue to move, new islands will rise while old ones sink. Chains will lengthen, arcs will shift, and the ocean will never stop remaking itself. The Earth is not content to leave its oceans empty. It fills them with these quiet markers of motion, these islands in the stream, each one a testament to the restless beauty of a planet always in motion. For as long as humans have walked the Earth, the ground beneath them has been both a comfort and a mystery. Solid rock, fertile soil, and steady land seem the surest of foundations. But when that ground trembled, cracked, or suddenly erupted with fire, people reached for explanations. Before seismographs and plate tectonics, there were myths, stories woven to make sense of a restless Earth. These tales gave meaning to chaos, turning quakes and eruptions into acts of gods, monsters, or spirits hidden below. In Japan, earthquakes were said to be caused by a giant catfish named Namazu. This enormous creature lay deep beneath the islands, wriggling in the mud. Most of the time, it was held still by the god Kashima, who pinned it down with a stone. But whenever the god's grip loosened, Namazu thrashed and the land above shook violently. Even today, images of the giant catfish appear in old woodblock prints, reminders of how people sought to explain the unpredictable jolts of their homeland. Across the Pacific in ancient Greece, it was Poseidon, god of the sea, who earned the title Earthshaker. With a strike of his trident, he could stir the ocean and rattle the land. For the Greeks, earthquakes were not just natural disasters, but divine messages, signs of a god's displeasure or power. To live in such a land of myths was to see the trembling of the ground as part of a larger cosmic drama, one in which humans were only small actors. Volcanoes too drew the imagination. In Italy, Mount Etna was said to be the forge of Hephaestus, god of fire and blacksmithing. The eruptions were the smoke and sparks of his workshop, where he forged weapons for the gods. The roar of explosions was the sound of hammers striking anvils deep within the mountain. In Polynesian tradition, volcanoes belonged to Pele, the goddess of fire and creation. Her fiery temper was said to explain eruptions, while her lava flows were the traces of her power carving new land. People honored her with chants and offerings, acknowledging the gifts and dangers of living on volcanic soil. In Norse mythology, the trembling of the earth was linked to the struggles of Loki, the trickster god. Bound in chains beneath the ground as punishment, Loki writhed whenever venom from a serpent dripped onto his face. His movements shook the land, sending quakes through Midgard, the world of humans. Even here, deep beneath icy mountains, the restless earth was imagined as a being alive with pain and struggle. The myths were not simply stories of destruction. They often reflected the double-edged nature of Earth's restlessness. Volcanoes could devastate, but they also created fertile soils and new land. Earthquakes could topple cities, but they also reminded people of the power of gods who protected or punished. By weaving disasters into myth, communities found ways to live with uncertainty, to respect the forces they could not control. Cultures from South America to the Pacific Northwest told of Earth shaking as battles between great beings below. In Chile, the Mapuche people spoke of the serpent Kai Kai, who ruled the seas, and her rival Tren Tren, who ruled the land. Their clashes caused floods, earthquakes, and the rising and falling of mountains. For the Haida people of the Pacific coast, earthquakes came from a giant bird, the thunderbird, whose wing beats shook the earth while battling great sea creatures. Each tale was a lens, turning the unseen mechanics of tectonics into vivid narratives that gave both warning and meaning. These stories also reflected a profound human need, the need to explain. To face a trembling ground or a mountain spitting fire without context would be terrifying. By giving names and faces to the forces, by imagining gods, spirits, or monsters behind the chaos, people could find order in disorder. A myth could not stop an eruption, but it could tell people why it happened, and perhaps how to appease the powers behind it. Even in more recent centuries, long after scientific inquiry began to replace myth, the need for explanation remained. In the 17th and 18th centuries, some Europeans explained earthquakes as punishments from God for human sins. The Lisbon earthquake of 1755, which devastated the city and killed tens of thousands, sparked fierce debates about divine justice. Was it punishment for wickedness or a test of faith? Philosophers, theologians, and scientists all grappled with the question, showing how deeply humans craved meaning in the face of disaster. Today we understand the mechanics. Plates grind, stress builds, magma rises, and pressure is released. But the myths still linger, woven into culture, art, and memory. The idea of a god of fire working beneath a mountain, or a restless serpent shifting the seas still resonates, even if we know the geological truth. They remind us of a time when imagination was the only tool available, when stories were the bridges between fear and understanding. There is also a curious parallel between myth and science. Both, in their own ways, are attempts to explain the same phenomena. The ancients saw catfish, gods, or serpents, where we see mantle plumes and subduction zones. Both are narratives, one poetic and symbolic, the other analytical and measured. And though science has replaced myth in explaining the mechanics, the human desire for story has not vanished. We still tell ourselves tales about the restless earth, only now they involve diagrams, charts, and theories instead of thunder gods and tricksters. The myths, however, retain their beauty. They remind us that long before satellites mapped the seafloor or sensors recorded tremors, people were paying attention. They noticed patterns, connected cause and effect, and sought to place themselves in the vast drama of nature. They knew, even without the word tectonics, that the earth was alive with hidden motion. To live on a restless earth is to accept both danger and wonder. Myths gave that restlessness a face, turning terror into story, uncertainty into tradition. Even now, when the ground shakes or a volcano erupts, it is hard not to feel the pull of those old explanations. Science gives us the how, but myth reminds us of the why, the human need to see meaning in a world that is never still. The trembling of the earth has always been more than a geological event. It has been a spark for imagination, a mirror of human hopes and fears, and a reminder that the solid ground we take for granted is anything but. Myths, in their way, honored that truth. They may not have described mantle convection or subduction zones, but they captured the essence of a restless planet, alive and unpredictable, always moving beneath our feet. The restless earth was once explained through myths of gods and monsters, then through the bold guesses of visionaries like Alfred Wegener. Today, however, we have tools of remarkable precision to peer beneath the surface and watch the plates move in real time. Geology is no longer confined to chisels and hammers in the field, though those remain useful. It now includes satellites orbiting far above, sensors listening deep below, and computer models capable of simulating millions of years of tectonic motion. To study the ground beneath our feet, we often look far beyond it. One of the most powerful tools is the humble seismograph. These instruments record the vibrations of the Earth, tracing out the wiggles caused by earthquakes, explosions, or even the subtle shifts of ocean waves. A single seismograph can capture the moment when stress is released along a fault, but a network of them spread across the world becomes something even greater, an X-ray machine for the planet. As seismic waves pass through Earth's interior, they bend, slow, or speed up depending on the material they encounter. By studying these changes, geologists can map what lies hidden, where slabs of crust are sinking into the mantle, where plumes of hot rock rise, and even what the outer and inner core are made of. Earthquakes, destructive as they may be, are also probes that let us glimpse the unseen layers of our world. Then there is GPS, a technology most of us think of as guiding cars and phones. For geologists, it is a way of measuring tectonic motion with millimeter accuracy. By planting GPS receivers on stable points across continents, Scientists can watch as plates drift at a pace of a few centimeters per year. The ground does not appear to move, yet year by year the data reveals its slow march. In California, GPS stations show the Pacific plate sliding north past North America. In the Himalayas, they reveal India still pressing into Asia, pushing the mountains ever higher. The continents may not notice their own journeys, but the satellites do, faithfully recording their wanderings. Satellites provide other insights as well. Radar interferometry, a technique using repeating satellite passes, can detect how the ground shifts after an earthquake or a volcanic eruption. By comparing images taken days or weeks apart, scientists can see land rising, sinking, or sliding, even by just a few centimeters. From hundreds of kilometers above, satellites catch the subtle flexing of Earth's crust, offering clues to where strain is building and where hazards may strike again. It is a perspective unavailable to past generations, as though the entire planet had become a living laboratory under watchful eyes. In the oceans, where most of the tectonic action happens, instruments have to work even harder. Seismometers rest on the seafloor, listening to rumbles that would otherwise go unnoticed. Robots explore hydrothermal vents along mid-ocean ridges, collecting samples of fresh crust and monitoring the chemistry of the waters. Submersibles descend into trenches to capture data on the deepest points on Earth, places that remain more mysterious than the surface of the Moon. The ocean hides much of the tectonic story, but technology is slowly lifting that veil. Despite all these advances, mysteries remain. One of the great questions is what truly drives plate motion. Mantle convection is the main engine, but details are elusive. Do plumes from the deep mantle rise like narrow columns, or are they broader, messier upwellings? How do slabs of sinking crust interact with the mantle as they descend? Do they stir the flow like paddles, or vanish quietly into deeper layers? These are questions scientists debate using computer models and seismic imaging to search for answers. Even the initiation of subduction zones is puzzling. Once a plate is sinking, the process sustains itself. But how does the first plunge begin? Some suggest plates buckle under their own weight. Others think external forces push them downward. Without knowing how subduction begins, we lack a full picture of how Earth's tectonic system started billions of years ago. Volcanoes and earthquakes, though better understood, still surprise us. We cannot predict exactly when or where the next great quake will strike. We can calculate probabilities, identify faults that are locked and ready, but the precise moment of release remains beyond us. Similarly, volcanoes may show signs of awakening, gas emissions, swelling slopes, rising tremors, but eruptions can still defy forecasts. The Earth, it seems, prefers to keep its secrets, revealing them only on its own terms. Another enduring mystery lies in the deep past. Plate tectonics as we know it has shaped Earth for at least 3 billion years, but before that the evidence grows hazy. Did early Earth operate with smaller, more chaotic plates? Was there a time when the crust was a stagnant lid, immobile above a hotter mantle? Understanding how tectonics began is crucial because it ties directly into how the planet cooled, how continents formed, and how life found a stable home. But the rocks that hold those answers are rare and often altered, leaving scientists to piece together clues like detectives reconstructing a crime scene long after it happened. And then there is the future. We know that continents will drift into new configurations, that a supercontinent will one day form again, perhaps Pangaea Ultima, but the exact path remains uncertain. Will the Atlantic close, reuniting the Americas with Europe and Africa? Will the Pacific shrink until Asia and the Americas collide? Or will an entirely different arrangement emerge, one we have not yet imagined? The plates are moving, but their final destinations remain unknown, part of a puzzle whose solution we will never fully witness. What makes the science of tectonics so compelling is its blend of precision and mystery. We can measure continental drift to the millimeter, yet we cannot say when the next quake will strike. We can map plumes rising through the mantle, yet still debate their origins. We can watch volcanoes awaken, yet still be surprised by their fury. Geology is a science of patience, one that deals in timescales far beyond human lifetimes, where progress comes from piecing together fragments of a vast and restless story. To study the earth beneath our feet is to listen to whispers and echoes. Seismographs catch vibrations, satellites watch from afar, and GPS marks the slow march of continents. Together they reveal a living planet, one that's endlessly reshaping itself. And yet, Even with our instruments and models, much of the story remains hidden, a mystery that invites wonder as much as it does explanation. The restless Earth has always moved. Now we can see it move, measure it, and even anticipate its moods. But it still surprises us, reminding us that some secrets lie deep, beyond the reach of even our most advanced tools. Perhaps that is part of the fascination. For all we know, there is always more to discover, always more hidden beneath our feet, waiting to shake the ground or raise the land in ways both subtle and spectacular. And so the science continues, listening patiently to the heartbeat of a planet that never truly rests. The continents may seem fixed, but they are always moving, carried on the slow drift of tectonic plates. In the grand timeline of geology, today's world map is only a temporary arrangement, one more frame in a film that has been running for billions of years. Just as Pangaea once came together and later broke apart, so too will our continents shift, collide, and reform into new configurations. To imagine the future of Earth is to picture a planet that will not resemble the one we know, with new oceans opening, mountains rising, and climates changing as the restless Earth continues its journey. Africa is already on the move. It drifts northward a few centimeters each year, slowly closing the Mediterranean Sea. In tens of millions of years, Africa will collide fully with Europe, squeezing the sea out of existence and raising new mountains where Italy, Greece, and Spain now lie. The collision may rival the Himalayas in scale, creating a new belt of peaks stretching across what is now southern Europe. Cities like Rome or Athens, if they still existed by then, would find themselves at the foot of mountains as tall as any on Earth. Meanwhile, the Atlantic Ocean, which has been widening since the breakup of Pangaea, may eventually begin to close. If subduction zones form along its margins, the ocean could shrink until the Americas and Europe and Africa meet again. Over hundreds of millions of years they could rejoin in a new supercontinent. Some scientists call this hypothetical landmass Pangaea Ultima, the next great unification of the world's continents. In this vision of the future, the familiar shapes of the Americas, Africa, and Eurasia are pressed together into one sprawling continent, ringed by a vast ocean. Other models suggest different outcomes. Some envision all the continents drifting northward toward the Arctic, creating a supercontinent dubbed Amasia. In this scenario, the Pacific continues to shrink, and Asia and the Americas fuse together at the top of the world. Another idea imagines continents reuniting across the Pacific, forming a supercontinent called Nova Pangaea. The details differ, but the theme remains. The map will change, the continents will not remain where they are, and Earth will continue its restless cycle of gathering and breaking apart. Whatever the arrangement, the impact on climate would be profound. Supercontinents disrupt global circulation patterns, changing winds, rainfall, and ocean currents. Vast interiors far from the sea would likely be dry and arid, while coasts would host narrow belts of fertility. Ice sheets might expand or contract depending on how the land clustered at the poles. Some periods in Earth's past supercontinent cycles were marked by icehouse climates, others by greenhouse conditions. The arrangement of continents is not just a matter of geography, it is a major driver of the atmosphere and the long-term balance of life. As continents collide, mountains will continue to rise. The Himalayas, already the tallest peaks in the world, are still growing as India pushes into Asia. Millions of years from now, they may stand even higher, their glaciers feeding vast rivers across the continent. New mountain chains will form wherever plates converge, in the Mediterranean, in the Pacific, and in future collision zones we can only guess at. These ranges will shape rainfall patterns, create new habitats, and carve landscapes that will endure long after our own time has passed. At the same time, oceans will open where land is stretched apart. In East Africa, the Rift Valley is widening, and one day seawater will flood in, creating a new ocean between the Somali Plate and the rest of Africa. Islands may rise along the rift's margins, just as Iceland straddles the mid-Atlantic ridge today. Farther afield, if continents continue to separate in other regions, new seaways may divide what is now familiar land. These shifts are subtle in our lifetimes but immense over the span of millions of years. And where does humanity fit into this story? On one hand, our time on Earth is brief compared to the movements of tectonic plates. Civilizations rise and fall in a matter of centuries, while continents drift only a few centimeters in the same span. In the deep future of new supercontinents and vanished oceans, humanity as we know it may no longer exist. Our cities may crumble, our monuments turn to dust, our species replaced or transformed by the long march of time. The Earth will not pause for us. It will continue to move, just as it has for billions of years. Yet in another sense, we are participants in this journey. We have learned to measure the drift of plates, to understand the mechanics of subduction and rifting, to map the ocean floor and study the deep mantle. We are the first species to recognize the restless nature of the ground beneath us, to see past the illusion of permanence. We build in earthquake zones, farm on volcanic soils, and live at the mercy of tectonic forces, but we also prepare, adapt, and marvel. Our knowledge of plate tectonics is part of our role in Earth's story, a way of seeing the planet not as static, but as alive. It is even possible that humanity, through its influence on climate and the environment, has become a geological force in its own right. Some scientists speak of the Anthropocene, an epoch marked by human activity. Our reshaping of landscapes, our emissions of carbon, and our engineering feats may leave traces in the geological record as distinct as any mountain building or volcanic eruption. In this way, we have joined the restless Earth as co-authors of its history, even if only for a brief chapter. The future of the restless Earth is certain in its uncertainty. Continents will drift, oceans will open and close, mountains will rise and climates will shift, but the exact details, the precise paths of the plates remain unknown. Will Pangaea Ultima form, or will Amalsia take shape instead? Will Africa's collision with Europe close the Mediterranean entirely, or will some fragment of sea remain? These questions remind us that the Earth is both predictable and mysterious, guided by cycles yet full of surprises. When we look to the future of our planet, we are reminded that maps are not permanent, that mountains are not eternal, and that even the oceans have lifespans. The continents are travelers, and we are simply passengers for a moment, carried along on their slow, inexorable journeys. The future Earth will be as restless as the past, a world forever in motion, sculpting landscapes we cannot yet imagine. And though we will not be here to walk its mountains or sail its seas, we can picture them, knowing that the ground beneath us today is only a temporary stop in the endless journey of a living planet. Time moves differently for the Earth than it does for us. Human lives are measured in decades, centuries at most, while the planet measures in millions and billions of years. To us, a century feels long, an empire eternal. To the Earth, such spans are little more than flickers, brief moments in a story that has been unfolding since fire first cooled into stone. When we look at the restless motions of tectonics, the patience of the planet becomes clear. Mountains rise not in years, but in eons. Oceans open and close over spans so vast that even the oldest human records cannot capture them. We live in the middle of a story too long for us to ever read in full, yet within that patience lies quiet power. The shifting of plates, so slow as to be imperceptible, has shaped every coastline, every valley, every range of peaks on Earth. It is the storyteller of the landscape, writing in stone rather than ink. The Himalayas are one of its chapters, the Atlantic Ocean another. The deserts of Africa, the rainforests of South America, the icy expanse of Antarctica, all of them bear the signature of tectonic drift. It is a story written with immense restraint, every sentence taking millions of years to complete. But when we step back and take in the whole, the narrative is grander than any history book, deeper than any myth. The patience of tectonics is easy to miss because it works on scales so far removed from human perception. The ground feels solid, unmoving, dependable. But if you could speed up time, the continents would flow like rafts on a pond, colliding, splitting, reshaping themselves in an endless dance. Mountains would rise like bread in an oven, seas would spread like ink across parchment, and the map would look less like a fixed chart and more like a kaleidoscope in motion. We catch only glimpses of this through earthquakes and eruptions, sudden reminders of the restlessness below. The true power of tectonics, though, is in its steadiness, its unhurried shaping of the world. For humanity, the challenge is to recognize our place within this immense timescale. Our cities, our monuments, our very species are recent arrivals. Stonehenge is only 5,000 years old, the pyramids just a little older. The Himalayas, by comparison, have been rising for tens of millions of years, and they are still climbing. The Atlantic Ocean has been widening for 200 million years, and continues even now. Against such measures our works are brief sparks, bright and fleeting, while the Earth's work glows steadily across eternity. And yet there is comfort in this. The Earth is patient not just in its changes, but in its companionship. While civilizations rise and fall, while languages are born and forgotten, the planet continues its quiet motions, providing a stage on which life can unfold. We may notice its sudden jolts, but the deeper story is one of constancy, a planet always alive, always moving, never truly still. To live on Earth is to share space with a companion whose rhythms are far older than our own, whose patience far outstrips our understanding. Tectonics is more than a mechanism of geology. It is the memory of the planet. Each mountain range is a record of collision, each trench a reminder of crust consumed, each ridge a story of renewal. Even the fossils locked in stone owe their places to drifting continents and rising lands. To read the Earth is to listen to the patient storyteller beneath us, a narrator who speaks in landscapes instead of words. The scale may be vast, but the message is simple. Change is constant, and permanence is an illusion. This perspective is humbling, but also inspiring. It places our struggles and triumphs in context, showing us that while we are brief, we are also part of something greater. The ground beneath us, though restless, is dependable in its patterns, steady in its cycles. It will continue to move long after we are gone, creating new worlds for new life. In its patience lies both mystery and reassurance. Mystery in how much remains unknown, reassurance in the knowledge that the story will continue. There is a poetry to this patience. Think of a river carving a canyon over millions of years, each drop of water doing almost nothing, yet together sculpting wonders. Plate tectonics works the same way, each centimeter of drift insignificant, yet across time it remakes the planet. The Earth does not hurry, it has no need. It writes its story slowly, and in that slowness lies its strength. To imagine the future of this patient planet is to imagine maps we will never see, supercontinents forming, mountains rising, oceans shrinking and expanding. Humanity's time here may be brief in comparison, but we are fortunate enough to glimpse a moment of this endless process. We walk on continents mid-journey, we live beside mountains still rising, we sail oceans still widening. We exist within the movement, and though we cannot see its end, we can feel its presence in every tremor, every eruption, every ridge beneath the sea. The Earth is restless, but it is also eternal. Its plates shift and grind, its mountains crumble and rise again, its oceans open and close. To us these motions seem imperceptible. To the planet, they are its very heartbeat. We are lucky to share in that rhythm, to live on a world that moves with such quiet purpose. And when we step back to see the bigger picture, we find not chaos but a patient planet, shaping itself with steady hands, forever becoming, forever telling its story in the language of stone.